been used long before computers showed up. Julius Caesar used what's now called a Caesar cipher to encrypt private correspondence. He would shift the letters in a message forward by 3 places, so A became D and the word Brutus became this. To decipher the message, recipients had to know both the algorithm and the number to shift by, which acted as the key. The Caesar cipher is one example of a larger class of techniques called substitution ciphers. These replace every letter in a message with something else according to a translation. A big drawback of basic substitution ciphers is that letter frequencies are preserved. For example, E is the most common letter in English, so if your cipher translates E to an X, then X will show up the most frequently in the ciphertext. A skilled cryptanalyst can work backwards from these kinds of statistics to figure out the message. It was the breaking of a substitution cipher that led to the execution of Mary Queen of Scots in 1587 for plotting to kill Queen Elizabeth. Another fundamental class of techniques are permutation ciphers. Let's look at a simple example called a columnar transposition cipher. Here we take a message and fill the letters into a grid. In this case, we've chosen 5 by 5. To encrypt our message, we read out the characters in a different order. Let's say from the bottom left working upwards, 1 column at a time. The new letter ordering, what's called a permutation, is the encrypted message. The ordering direction, as well as the 5 by 5 grid size, serves as the key. Like before, if the cipher and key are known, a recipient can reverse the process to reveal the original message. By the 1900s, cryptography was mechanized in the form of encryption machines. The most famous was the German Enigma, used by the Nazis to encrypt their wartime communications. As we discussed back in episode 15, the Enigma was a typewriter-like machine with a keyboard and lampboard, both showing the full alphabet. Above that, there was a series of configurable rotors that were the key to the Enigma's encryption capability. First, let's look at just one rotor. One side had electrical contacts for all 26 letters. These connected to the other side of the rotor using cross-crossing wires that swapped one letter for another. If H went in, K might come out the other side. If K went in, F might come out, and so on. The letter swapping behaviour should sound familiar. It's a substitution cipher, but the Enigma was more sophisticated because it used 3 or more rotors in a row, each feeding into the next. Rotors could also be rotated to one of 26 possible starting positions, and they could be inserted in different orders, providing a lot of different substitution mappings. Following the rotors was a special circuit called a reflector. Instead of passing the signal on to another rotor, it connected every pin to another and sent the electrical signal back through